All right, so today we're talking about Ampere's law. What I'd like to do is walk you through a sort of derivation of the law, just so you're comfortable with it. We don't derive this law at this level. You can derive it in second and third year if you ever take those courses that derive it for you. But basically, what I'd like you to do is think with me as I'm developing this makeshift derivation. Let's say we have a long line of current I flowing in it, and we would like to see what the field looks like around this line. We know from the use of our law that the field over here will be given by direction of the field given by ds cross r hat. ds is this way along the current. R hat is going to point to where the point of observation is, and the field direction is given by the cross product, ds cross r hat, and field is going to go into the board. Over on this side, the field is going to come out of the board, ds r hat be that way. What you can do is line up your thumb with the current and use the right hand curl rule, and that gives you the direction of the field all around the conductor. What I'd like to do next is draw what the field looks like all along this contour that we've created. And I'd like to draw along this contour as well elements of length dl that are elements of length along the contour. And I will label this as B. So the field and the elements of length are always parallel. Symmetry is a very important concept in Ampere's law, same as Gauss's law. It's a central concept, and we'll see how to use it in this regard shortly. For now, what I'd like to do is calculate the integral of B dot dl around the closed contour. In Gauss's law, the equivalent of that was called the flux. Here is just called the line integral. We'll see why this is important in a couple of minutes. But for now, let's just play the game of wanting to calculate the integral of B dot dl around the closed contour. That is going to be the integral of B magnitude, dl magnitude, cosine the angle of between BL and B and dl, cosine theta. And that angle is going to be 0 because of the symmetry, because of the way we've chosen things. We've chosen to create a contour, this in red, right? And the elements of length dl point along this contour. So what you have now is the field pointing this way, but this is also your contour around which you're evaluating the integral. So if I go around this contour, I notice that the angle between B and dl is always 0. So the cosine of theta is 1, right? And that's going to be the integral of B times dl over the closed contour. Right? Again, the importance of this business of integrating B over the closed contour, B dl over the closed contour, will become obvious hopefully in a few minutes. But what is the value of that integral? What do we know about the field from a long line? From the use of our law, we found out over 2 pages of derivation that the field a distance r away is equal to mu naught I over 2 pi r. That's for a long conductor. We did the derivation for a short conductor, and then we extended the limits of integration, allowing the line to go to infinity, to be very long. If B is given by that, then what is this going to be? That's going to be equal to the integral of B, which is equal to mu naught I over 2 pi r times dl. Okay? And don't worry about the integration limits. pretty straightforward right now. What is constant in this case is mu naught comes out of the integral, I is constant, 2 pi, r is constant. This is the integral of dl around the closed contour, and that's simply what? What is the integral of dl around the closed contour? Is the sum of the l's around the contour, and that's just simply equal to 2 pi r. So that's going to give me mu naught I over 2 pi r multiplied by the integral of dl around the closed contour is also 2 pi r, and that's going to give me mu naught I enclosed. So the integral of b dot dl around the closed contour is equal to mu naught I enclosed. Okay, we have kind of not really derived Gauss's law, but we have set things up in such a way that the calculation of the integral is easy. And you can see that going forward, we're going to be, in a similar way to what we've done in Gauss's law, we're going to look at symmetry in such a way that it allows us to calculate this integral. Right? We want a field for this integral to be easy to calculate, just like in Gauss's law. We want a magnetic field that is uniform over the contour that we calculate, and such that the angle theta between B and the elements of length is going to be either 0 or 90 degrees. In this case, it is 0. Right? So what we have come up with is a statement of Ampere's law. It says that the integral of B dot dl, if you have a current anywhere, see, right, we have derived it, come up with, calculated the contour integral for a specific case or a special case of an infinite line and a loop that is a circle around the line. But what Ampere's law say is exactly this, that the integral of b dot dl around any closed contour is equal to mu naught times I enclosed. So what that means now, guys, is that this doesn't apply, the law doesn't apply only for the case of a long line and a circular contour. Just like we did with Gauss's law, we derived it for a point charge with a spherical surface around it. Right? The statement of the law that can be proved later, you can look into the proof on your own if you want, is that if there is, any current flowing, right, and you take any closed loop around it, right, and if you're crazy enough to go and calculate the field from the current along the loop, and maybe it looks something like that, B, and if you were to take an element of length, along the loop over which the field direction and magnitude does not change appreciably, dl here, and if you were to calculate the angle between B and dl all around the contour, angle theta, and you were to, you were crazy enough to go and find the field at every point along the contour, find an element of length dl over which, small enough over which B does not change, and find the angle between B and dl, theta, and calculate the following sum over I, or integral of B dl cos theta. What you're doing basically is summing. So what you're doing is saying B dl cos theta plus B dl cos theta over, this is 1, this is 2, this is 1, this is 2, and so on and so forth. This is not exact, okay? In the limit that sum, which should really be using delta L here. We're just doing a hand-waving argument right now to remind you that the integral, or remind us that the integral is nothing but a sum. If I were to be crazy enough to calculate the sum of B dl cos theta all over the contour, which is in effect taking the integral B dl cos theta over the contour, right? If I were to go and add all these bits up, B dl cos theta, B dl cos theta, I will end up with mu naught I enclosed, right? So if I had another current flowing here, right, like that, down, and this I up, I down, then the integral of B dot dl around this closed contour will be 0, because I enclosed is 0. Right? I'll expand on that in a little bit. I'm going to erase this board. We have limited space in the way we've set things up. I'm trying to maximize you seeing me and, find an optimal situation where you can see me while I'm doing this and you can see what I'm writing. So the statement of Ampere's law is the following. The integral of B dot dl around the closed contour is equal to mu naught I enclosed. Okay? Let's take the example of, let's say our contour is nice and simple like that, right? And I have current I flowing this way. And current I flowing this way, here. So I goes up here and goes down here, okay? Along this contour, the integral of B dot dl around this closed contour is going to equal to mu naught I enclosed. If these currents are the same, then in this case, I enclosed is 0. So if I enclosed is 0, then the integral of B dot dl is equal to 0. Right? So what does that mean? If I were to actually calculate what the field looks like here over elements of length over which the field does not change, find the angle theta between B and dl, and multiply all that out and add it up, I'm going to end up with 0. Okay, fine. The contour integral, which in Gauss's law would have been called, the equivalent to that would have been called the flux over, surface integral. The contour integral is 0. Does that mean that the field is 0 along the contour, along the loop? No, of course not. Because of the lack of symmetry here, in that these two lines are closer to this point than they are to this point, right? We cannot say that the field is going to be 0 along the contour. It might be 0 at some point along the contour, right? But the field will not be necessarily 0 at every point along, for sure, not be 0 for every point along the contour. This is a similar case to Gauss's law, whereby the flux can be 0, but the field is not 0. Right? So this is something to pay attention to, conceptual understanding of Ampere's law. We're going to now use Ampere's law and there are limitations on Ampere. Just like Gauss's law, there were limitations on what you can use it for in terms of calculating fields. The law is valid. Gauss's law is valid. It applies. It holds everywhere. That was part of the discussion you had on the midterm. We asked you slightly tricky questions. Wanted you to distinguish between the applicability of the law, the validity of the law, and the ability to use the law to calculate fields. The same thing applies in the case of Ampere's law. The symmetries, the prominent symmetries, only 3 symmetries that we use Gauss's law for to calculate fields using Gauss's law were spherical symmetries, like a point or a sphere with uniform charge distribution, for example, a long line of charge, and an infinite plane of charge. These were pretty much the only symmetries that you could use Gauss's law to calculate fields. In the case of Ampere's law, also there are limitations. We have to keep in mind that when we talk about symmetry in the context of Gauss's law, the requirements were what? I mean, we talk about a cube being symmetrical, or a square being symmetrical, or a short cylinder being symmetrical. The only 2 meaningful outcomes of symmetry for Gauss's law were that the field around the surface had to be uniform, and the angle between the field and the area element had to be either 0 or 90, constant. Not just constant, but we looked at situations where the angle was either 0 or 90. And that made the calculation of the surface integral easy, the flux. And that allowed us to calculate the field. We could take the field out of the integral. Okay? The whole point behind symmetry is being able to take the field out of the integral so you can calculate the field E in Gauss's law. The same thing will apply in this case. The simplest case, we're going to, let's say that we do not know, okay, Biot-Savart law. All we have is Ampere's law, okay? So how do we use Ampere's law to calculate fields. We kind of did things so far backwards in that we used Ampere's law, so we used the Biot-Savart law, our knowledge of the field, to kind of prove Ampere's law for a very simple current distribution that is a long line with current I flowing in it along a very, very intuitive contour, which was a circle around the line. So let's say that we do not know the Biot-Savart law. We have a current I flowing in a long conductor, and we'd like to use Ampere's law to calculate the field, the distance r away from this current. So what do? Well, we know Ampere's law. We don't know the Biot-Savart law today. We say that the integral of B dot dl around the closed contour is equal to mu naught I enclosed. And this is your first practice with Ampere's law. We have to create a contour along which the calculation of the integral B dot dl is easy, which allows us to take B outside. We don't know the value of B, but we know a little bit about magnetism in that the field will point this way. Right? Let's accept the fact that we know that. And if that's the case, and we know that the field is going to take a circular profile around the current, then the loop that we create should reflect and respect that symmetry. So I'm going to create a circular loop like that. This is going to be my contour. And along that contour, I'm going to draw my field lines. The field lines would look something like this. B, 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 that'd be nice B, and B, B. And we already know what we're going to do because we've done it. And I'm going to create my length elements around the contour dl. And I'm going to apply the law. So that says the integral of B dot dl is equal to mu naught I enclosed. Okay, along the closed contour. We were smart about the way we picked this. We knew we just did it over there, but starting with the Biot-Savart law and trying to come up with Ampere's law. What we had done there was seeing the importance of on the previous board. I'm used to having two boards. Seeing the importance of picking loops that are, sorry, power just went out. All right, good, we're back on. We're seeing the importance of picking a current loop, picking a loop over which the magnetic field was uniform and parallel to the loop. So, and this is what we applied in this case. So knowing what we had done before, knowing the profile of the field, we've created the loop over which B is uniform and B is parallel to the loop. So in this case, the integral of B dot dl becomes B dl cosine theta equal to mu naught I enclosed. Okay? And theta, because of symmetry, because by design, is going to be 0. That becomes the integral of B dl. I'm dropping the magnitude bars in this case. That's equal to mu naught I enclosed. And well, B is because of the loop we have picked, and you got to think about that with everything that you do with Ampere's law, just like you did with Gauss's law. B is going to jump out of the integral, and you're left with the integral around the contour, closed contour of the L equal to mu naught I enclosed. Okay, and that's going to give you that. Well, B integral of dl on a closed contour is 2 pi r equal to mu naught I enclosed. And if you do not know the Biot-Savart law, you've got that the field is equal to mu naught I over 2 pi r, which again took us 2 pages to derive, after which we had to take the limit of B as the length of the conductor went to infinity. And now we got it in pretty much one line. So this is the first thing we're using Ampere's law for, to calculate the field from a long line. What I'm going to do next is a few examples using Ampere's law, perhaps to focus a bit on the conceptual aspect of Ampere's law as much as possible. let's say now that I have a, let's play some games with Ampere's law. So this is an example. Remember current density. Current density, if it's uniform, is equal to what you have. If you had current density J flowing through an area where the area vector looked like this. This is the ds, right? This was J. We said that the current flowing through that area is equal to, well, that's the current density, it's like that, it's angle theta. The current is a scalar given by the integral of J dot ds or dA. Okay? So if the current density is uniform, then I is simply equal to J times A, okay, where A is the area of the area through which the current density is flowing. And you can say also that J is equal to I over A if J is uniform. If not, you have to integrate. Okay. So J is given in amps per meter squared, current density. But it doesn't always have to be given in amps per meter squared. For example, remember that in electrostatics, we had current densities that looked like what? If you had current density over volume, we called it rho v, right? And you had current densities over area called rho s, and current densities over length, linear current density, sorry, charge densities. We had a charge density, not current density. If you had a charge density over a volume, we call it rho v. A charge density over an area, you call it rho s, and linear charge density, you call it rho l. So typically J is given as amps per meter squared. But let's take the following example, whereby I have a really long sheet. Sheet is infinite in this dimension, this way, and infinite in that dimension as well. And I have current density J flowing through the sheet. Now this sheet will have width in examples later on, but for now it's just a thin sheet. So I got a thin sheet of current. Current J flowing into the board, right? So I is flowing into the board. Later on, we're going to get an example whereby the sheet is thicker. So when the sheet is thick, like let's say it's long this way and long that way, but it has some thickness here, then the current is equal to J times A if the current density is uniform, or integral over J dot dA. So in this case, J is given in units of amps per meter squared. Right? However, in this case, because so let's say total current I flows through the sheet is long this way, wide this way, and long this way, and total current I flows through the sheet. The current density is given J in what now? Because the sheet is thin, amount of current flowing through the sheet is going to be given by I is equal to integral of what? J dl in this case, right? So the current density J is given in amps per meter. So if you take an element of length dl and you have current density J flowing through it, then the current di is given by J dl. Okay? So what we'd like to do with this current sheet, now we've talked a little bit about current density not being amps per meter squared because it's a thin sheet. In the case of a thicker sheet, which has width, it'll be J given by amps per meter squared. In this case, it's just amps per meter. If I have this infinite sheet in this direction and that direction with uniform current density J flowing through it, what would the field be at this point, let's say? Right? So what I'd like you to think about for the next, next few seconds is how are you going to use symmetry to your advantage and Ampere's law to calculate the field at this point here? What kind of, we're going to use Ampere's law, so we need what? The integral of B dot dl allow the closed loop to be equal to what, mu naught I enclosed. So just like with Gauss's law, there are two elements to the calculation. First, you have to calculate the contour integral, line integral, and you have to calculate I enclosed. Okay. Usually they're pretty straightforward, but they can become complicated if you, if the geometry is a bit more involved, or we introduce another sheet, let's say somewhere, things can get really interesting. So, what kind of loop am I going to choose to calculate my contour integral over, or line integral over? And remember that think about it for a second. And keep in mind, just like in Gauss's law, we're looking for symmetry in the context that we want. I mean, again, a square is symmetrical, a short cylinder is symmetrical, rectangle, parallel pipette is symmetrical. But when it comes to symmetry in Gauss's law, we're looking for two things. One, the field being uniform along the Gaussian surface. Two, the angle between the field and the area vector being constant, and specifically either 0 or 90 degrees. One more time. The only two meaningful things that we get out of symmetry, we look at symmetry around us. There's lots of symmetry. Symmetry in terms of a cube, in terms of a square, in terms of all these things are symmetrical. But the useful, meaningful, applicable properties of symmetry for Gauss's law are only two things. One is that on your Gaussian surface, you need the field to be uniform, and on your Gaussian surface, you want the field to point along the same direction as the area vector or perpendicular to the area vector, and we've done both. In this context, this is the same story. We need to create an Amperian loop, call it an Amperian loop. In Gauss's law, we call it the Gaussian surface, you call it an Amperian loop. We need to create a contour Amperian loop over which what? The field is parallel to the loop. First, field has uniform magnitude over the loop, and the field is parallel or perpendicular to the loop. So we're going to use, we don't know what the field looks like here, but because of symmetry, because of what we've seen, we can at least tell maybe that this guy here, this current element is going to create a field this way, like at this point it's going to create a field, pointing this way, down that way. And from this guy here, you're going to create we can more or less tell that the field profile is going to look like something like this over here. And we don't know if, I'm drawing it this way, but we really do not know yet if the field is going to be stronger here than there or whatnot. It's an infinite sheet. We saw, the example of an infinite sheet with Gauss's law. When we had an infinite sheet, the field didn't change at all if you moved away from the sheet. If you moved, this is you have a sheet here, and you're looking at the field near the sheet. If you move this way along the sheet or that way, the field didn't change. But most importantly, if you moved up or down away from the sheet, the field didn't change either. That was very peculiar. Here, we don't know. We're not sure. Is the field going to be stronger here than there? I'm not sure. Maybe let's draw these vectors a little bit bigger to indicate the possibility of the field being bigger closer to the current source. We're not sure yet. But what we do know now is that we need a loop, right? The main thing about the loop is that because of symmetry, we can tell that B is going to be pointing this way, and the magnitude of B is going to be the same along this line, let's say. So my first part of the loop, respecting the idea of symmetry, is going to look like this. Why? Over this part of the loop, B is parallel to the loop and B is uniform. Now I need to continue to close the loop. So what am I going to do? From here, if I go this way, that's a good thing to do. Why? Because, the field strength might be changing this way. We don't know, we're not sure. But we don't care because while DL points this way, parallel to the field here, DL is going to be perpendicular to the field here. And we said that the requirements for symmetry are that B be either parallel or perpendicular to the element of length that we choose. This makes our life easy because B dot DL is 0 here. And down below, the field looks like maybe something like this. Stronger, maybe, closer to the sheet, we don't know. We'll find out soon enough. But we know that at least if we pick a loop that is symmetric above and below, then the field here let me complete the picture. do one more here for fun. This is B, and this is B. And what we've done now is we've created our loop over which the line integral is 0 here because B dot dl, B is this way, and dl is that way, and B dot dl is B dl cos 90, 0, 0 here, 0 there, 0 here, 0 there. What this reduces to is the integral of B dot dl over here and B dot dl over there. Right. So let me pick a loop of length little l, and with w if you want, which doesn't matter in this case. Okay. So I go now to the integral of B dot dl, and on my, well, square loop in this case, equal to mu naught I enclosed. Okay. So what is this integral of B dot dl? Here is 0, here is 0, I have here and there to worry about. What is it reduced to? Over here is B dl cos theta. B is that way, and dl is that way. Theta is 0, cos theta is 1. That becomes B times dl. Integrated over the length, B comes out, that becomes BL. So on the top of the loop, at the top of the loop I have BL. At the bottom of the loop I also have BL. And what is it here? Well, look at here. It's not minus B dl. B is this way, and dl is that way. We're taking the loop in this direction, right? We've chosen to take the loop in the direction of the field, right? So B dl here is B times dl integrated over the length. L gives me just BL because B is uniform. And what is this? This is a sum of, remember, the integral is nothing but the sum, BDL plus BDL plus BDL. You take B out, DL plus DL gives you the length. So I got one of those up there, one of those down there. So it is, and remember, because the angle, what matters is not the fact that they're pointing this way. What you care about is the angle between these guys. So what we're looking for is B DL cos theta, B magnitude up here or down here, DL magnitude up here or down here, and cosine the angle between them, and that's always going to be 0 up here and down there. So it's going to be BDL integrated, it's going to be B times L. So there's two of those, so that's 2BL equal to mu naught I enclosed. And now the second part is calculating the I enclosed. What is I enclosed? Because uniform current density, we need the uniform current density. Well, not just because it makes the calculation easier for I enclosed, but also if the current density was uniform, the field profile would not look like this, and we would not be able to use Ampere's law. Ampere's law always applies. Ampere's law is always valid. It is, Ampere's law is true everywhere, except that we would not be able to use it in this case necessarily if the current density was uniform. So how much current is enclosed in here? Just remember, like we did with when we looked at the infinite sheet with Gauss's law and had a parallel pipette or a cylinder sticking, from both sides. How much charge was enclosed? The charge enclosed was rho s multiplied by the area of the parallel pipette or the cylinder. The same here, because J is given in units of amps per meter. Right? If this is a thin sheet, remember, in the case of a thick sheet, it'll be amps per meter squared. We'll have current here and there, current density, and then your total current in a given area is J times A, or integral of J dot dA. In this case, the current enclosed is simply L times J. So 2BL is equal to mu naught times J times L. So B is equal to mu naught J over 2 in a very similar fashion to calculating the electric field from an infinite sheet. And that was given by rho s over 2 epsilon naught. Now, magnetic materials, just like, with dielectrics, we have magnetic materials, mu. When we were talking about dielectrics, we replaced epsilon naught with epsilon. The same thing happens here. When you have magnetic materials, you're going to have to replace mu naught with mu. And mu is equal to the permeability of a material is given by the relative permeability multiplied by the permeability of free space. So again, the permeability of a material is given by the relative permeability multiplied by the permeability of free space. All right, moving on to another example. And my focus now, having covered Ampere's law, is to give you as many examples as possible over the next couple of days before we move into Faraday's law. And by the way, what we have is 2 weeks worth of lectures, a little bit more maybe. The first week is going to be Ampere's law, the second week is going to be Faraday's law, and a little bit of inductance towards the end, but you would have covered the whole course material. So we have to keep moving to keep the lights on in the room. We're kind of okay. We're going to take a pause here.